Right. We now come to the third example in Klepner's book, and this is on page number 265. So, this I think should be one of the most important examples for a person who's doing this topic for the first time. Page 265, edition 1, Klepner and Kolenkov. And this particular problem is solved by at least three methods. I mean, they're quite similar to each other, but nevertheless, um, it's good to call it three different methods, and we got plenty to learn from each of these methods. So let's go slow on this. What is the problem? I'll come to it in a minute, but before that, can we just quickly go through the formulae that we are interested in? This by far is the most important formula because it is the law, okay, and a similar formula that we learned long ago, and we're referring to the system. So let me save some time. Now, these are the two laws, and everything comes from these two laws. And these lead to two equations, one for translation, and which is that we're talking about rigid body, and we're talking about translation plus rotation. So the translation equation, we are very comfortable with this. This is equal to mass into acceleration of the center of mass. We're going to use this big time in this problem. So this is the first part of the problem coming from this law, and this law we've now translated to tau cm is equal to I cm alpha, and this is the rotation, pure rotation as seen through the eyes of an observer traveling along with the center of mass. And let's stick to the case. Okay, so now there are two more formulas that we have come across, and maybe it's worth writing them down as a revision. One is that the torque, how does one calculate the torque? Well, one first of all needs the origin, needs to know what the coordinate system is. Now we're going to emphasize on this as we try all the three methods, but once you have an origin and the coordinate system, yes, this is not a big deal, and it is equal to, okay, let's stick to tau z, and on the system of this rigid body is equal to RCM cross F external, okay, plus tau center of mass z. So we are assuming all the forces are in the xy plane. Now this formula is also an important formula, but this perhaps is the one formula where we haven't really worked out the simplification of the proof, but it's important for you to keep using this. Very nice formula. There is a translational component of the angular momentum, and there is a pure rotation part of the angular momentum, which looks so much like the pure rotation. It is looking exactly like the pure rotation formula. Omega at that instant is the rotation of that object about the center of mass, and as it appears to the eyes of the observer. Okay, traveling along with the center of mass. So this is the other formula that we have derived, and we've been writing this formula multiple amount of times so that it gets into our memory bank. And this problem will give us an opportunity to use each of these formula in each of the methods. So what is the famous formula? Now there is an inclined plane. Mind you, this is fixed, okay, and now for the first time, instead of a particle that is coming down the inclined plane, we have object which perhaps is a disc or a drum and appears as a circle from one point of the view, and I couldn't have drawn a worse diagram because it should really be touching only at a single point. And let me try to be better. Okay, so here it is. Here's a disc, there is a center, and this disc is coming rolling down the inclined plane, and we need to see what predictions we can make. Mind you, this is not a particle, it's a rigid body. and therefore you see both rotation and translation, and there are predictions which you can make. And the statement of the problem says that there is no slip. What does that mean? We'll come to that in a instant. No slip or rolling without slipping throughout its motion. And let's analyze the problem. So before we get to that, the first point to be made is, can we choose a coordinate system? I think I'll choose this as my coordinate system because the fact that the inclined plane is actually at rest. So this can be my x-axis and this can be my y-axis, and the z-axis is coming out of the plane of the board. The other important aspect is that this angle is given. The book says it's theta. Very good. Now, for a newcomer, it's very important to realize that, or intuitively, it's obvious that it's rolling like this as it's coming down. Now, because of this, this rolling is due to a friction force. And why am I confident about it? I'll get to that by actually completing the free body diagram. Now, when I draw the free body diagram, what I realize is that there is this force which is acting through the center of mass, that is mg. Now, the book calls it W, but let me just call it mg, and we are comfortable with this. There is a normal reaction which is also passing through the center of mass, that's n, and there is this we already know that this angle is theta. Okay, we'll need it for the resolution. Now there are only three forces, n, and then you have mg, and very important to make this observation that both of them pass through the center of mass. In other words, the torque, now we believe in this equation, tau cm is equal to ICM alpha, and these two forces, n and mg, do not contribute to the torque. So therefore, there is no turning torque, there is no rotation caused by these two forces. And in other words, if there is no friction, okay, if there is no friction, let me just write it clearly here. If there is no F, where is it? If there is no F, that is the friction force, there is no tau cm, implies that if it's not rotating initially, then it can't rotate. I mean, assuming that initially there is no rotation, it starts from rest, then it can't rotate about center of mass. Now this is a very important and nice conclusion, and it's based on our belief that this equation is right. So what I'm trying to say is that I'm pretty convinced of the existence of F if somebody is going to say that there is rolling without slipping, or for that matter rolling. So yes, this is the first conclusion. F exists. So let me just write it on the next page. For sure, F exists in this problem. So if it is a smooth frictionless surface, then you won't see this phenomena of rolling without slipping. But the second interesting conclusion is, and this is very important, F need not be equal to mu n. And the reason is that there is no slip. Okay, so there is no relative motion between the point of contact of the drum and the inclined plane. So you can't be sure that the friction force has exceeded or even reached its maximum possible value, which happens to be, from our previous understanding of mechanics, equal to mu n. So we can't be sure that what is the value of F, and now you'll be interested to know that will this cause an issue? Apparently it doesn't, so we'll come to that. But it's important for you to first keep these two things in mind. Now when you don't know the value of f, you just leave it as f. And so now we'll have a look at our free body diagram again, and this time things are getting slightly better. We happen to know all the three forces, but more importantly, we've reached a conclusion that F is not equal to mg, but it exists. Mu mg, sorry, and but it definitely exists, and perhaps in this direction, because intuitively we feel that it's going to roll like this, and the rolling is caused by friction, so it has to be a clockwise torque, and a force in the opposite direction will not give a clockwise torque about the center of mass. So far so good, and we've got everything on the board, and now we've got to use all the laws. This angle is theta, so let's use our first law, and once again let's take our time in making sure that we got all our axes and also the observer in place. And what does the observer see from the first equation? He says that Fx external is equal to mass into acceleration in the x direction. How good is that? So easy to use this, of the center of mass. Okay, so what is the force in the x direction? N does not contribute. F contributes. Very nice. Minus F. I'm also adhering to the sign convention. Minus F. Very good. And now mg has a component in this direction. Okay, mg has a component in this direction, and then also in this direction, and this component is along the x direction, which is mg sine theta. So minus f plus mg sine theta is equal to m into acceleration in the x direction, and this is definitely equation number 1, and very nice equation. Okay, good, we're on our way. What about the y equation? Perhaps I'm not so sure it's useful in this problem, but let me just write it anyway. N minus, actually it's not useful in this problem if I'm right. N minus mg cos theta equals to m into ay, which happens to be 0, so 0. N minus mg cos theta is 0. Okay, not very useful, but I think it's not very useful. So this is equation 2. But we have not exhausted our equations, and my third equation is something that I've not used a lot till now, but this is the third equation is, and just let me just write it here, tau cm is equal to ICM alpha, and ICM, by the way, we do happen to know ICM. Okay, let me just write it down. You can get it from anywhere for a disk, m r square by 2. Okay, so the third equation is tau cm. Now tau about this point, okay, n does not contribute, mg does not contribute because they both pass through the center of mass, but Mr. F, and I'm going to now stick to the sign convention, Mr. F is clockwise, so it's going to be minus F, okay, minus F R, okay, is equal to ICM and alpha. Okay, now alpha is unknown, but I do know the direction of the friction force, so this is going to be my third equation. Right, now it seems to me that I should write down these equations on the next page again, so that it's very clear to you. So let me write it down. Minus F plus mg sine theta is equal to mass into acceleration in the x direction of the center of mass. Okay, then I think the second equation is not useful, so I'm going to just go ahead and not write it at all. But the third equation is minus Fr is equal to ICM, which is known, into alpha. So here you go, there is an issue now. We're just trying to find out what the unknowns are. And the unknowns are F, then AXCM, and alpha. Okay, so there is an issue because there are only two equations, 1 and 2. Okay, well, perhaps you already guessed. We are nearly home. These two equations are correct, and all that matters is there is a rolling without slipping, which needs to be expressed as a constraint equation. And once I do that, I'll definitely have two equations which are already there here, plus one constraint equation, and then we have 3 unknowns and 3 equations, and you can solve them and make sure that you get the answer in the book. So great, things are looking great, and the only thing that remains is to discuss this constraint equation, and we are done. So I can take it easy now and do this slowly, because somewhere I get the feeling that we're doing really well. We got almost everything that we want, and let me see if I can do the constraint equation in a convincing way. Mind you, the axis is clear. Just want to remind you that you should keep an eye on what the unknowns are. Okay, the unknowns are A, and then okay, and also alpha, and also F, the magnitude of the friction force. The direction of the friction force is known. Right. So let's see, what is the constraint equation? Okay, the constraint equation is the velocity of the white point, okay, which is the white point on the disk, which is in contact at that freeze time, my favorite phrase, freeze time. And at that instant of time, the white point and the yellow point, which is actually a part of the inclined plane, have the same velocity with respect to the eyes of this observer who is standing on the inclined plane. Now this observer says that the velocity of the yellow point, without a doubt in his mind, velocity yellow point equals to 0. Now what is the velocity of the white point for the same observer? So let me write it down. Let me convince you that now I'm following the sign convention. Velocity of the white point, okay, is equal to okay, now watch this. I'm just adhering to the sign convention, is equal to VCM. Okay, now I'm going to do something which you might be slightly uncomfortable, but believe me, I think it's correct. VCM plus alpha times, oh, what a bad mistake, omega, I'm sorry, VCM plus, I'm sorry, please CM plus omega times r, okay, plus r omega. Right, now VCM is the velocity of the center of mass, and omega r is the velocity with respect to the eyes of the observer who's traveling along with the center of mass. So the two add up to give the velocity of the white point with respect to, what should I say, the observer who's just standing here. Okay, now the reason I'm putting a plus sign here is like this. Okay, by the way, omega is sort of unknown for me. Now, if omega is positive, that means it's rotating like this, anti-clockwise, then uh, then the velocity is positive. Okay, so if omega is positive, the velocity is positive, and that is why I put a plus sign, and it adds up to VCM. So let me just go ahead with this. I'll just convince you at the end. Now this equation is the constraint equation. Oh, by the way, this is equal to 0, and therefore this is equal to 0. And now I am going to write down the constraint equation. VCM plus R omega equals to 0. Okay, but that's not the equation I want. I want a relationship between ACM and alpha, and you know how to do that. Just differentiate this. So you just differentiate this, and what do you get? ACM plus R alpha equals 0, and that means the constraint equation is ACM equals to minus R alpha. Okay, now this is the constraint equation by sticking to the sign convention. And now how do I convince you about this? I'll convince you that this is right purely by arguing in the real example, but I just want you to note that I've written down all the equations by following my sign convention, adhering to my sign convention. So this is the third equation. Maybe I should write it down here. So I'm going to write it down here. ACM is equal to minus R alpha. This is equation 3, and for all practical purposes the problem is done, but I've got 3 equations and 3 unknowns. But I want to return to this equation to convince you that it is right. So let me do this last part again. Right in terms of the sign convention. So let me do that once. So here I have a object, this particular object. Now if this object with respect to the coordinate system that I have already drawn, which is y, x in this direction, z in this direction, y. Now if the acceleration happens to be in that direction, and it turns out to be positive, believe me, alpha will be like this, increasing the omega in this direction. Okay, it rolls faster and faster in the clockwise direction. In other words, alpha will be negative. In other words, what I'm trying to say is that from this picture itself, or from what we imagine as a motion, if ACM is positive, alpha is be negative, because clockwise is negative for us in our sign convention. And now you see that the equation respects this understanding that we have, that ACM is minus of R alpha. So magnitude of ACM doubtlessly is magnitude of R alpha, but you see, if A is positive and alpha is negative, then the equation sums up to be a meaningful statement. So that is why I was very confident that I got my constraint equation right by following my sign convention. Now I'm not doing the algebra, but the algebra gives me that I'm going to look into the book to write down the answer. It's very interesting. Oh my god, the book is not giving the value of f, but if you want, you can calculate the value of f. Okay, the value of f is equal to what is not given in the book, but the equations are sufficing to give you the value of f. The book seems to be very keen on telling you what is a, but I would also be interested in the value of the F, okay, the friction force, which is not equal to mu n. And so if you can see the consistency check here, F cannot be more than mu n, And indeed, if f required is more than mu n, then you can expect a classic phenomena called slip. We'll come to more and more of this phenomenon somewhere along the line, but the most important answer seems to be the value of a, and it's a very interesting answer, 2 by 3 g sine theta. The reason it's interesting is because when it was a particle, and we did this problem long back, we got the acceleration as of the center of mass, particle acceleration as g sine theta. And today we have a drum which is rolling and slipping, and the acceleration of the mass is 2 by 3 g sine theta. And what is interesting is that we can conclude from this, I think, please don't agree with me if you don't think I'm right, but this should be a fairly straightforward prediction. If you have a particle who's racing against a disk, okay, to me it seems like the particle is race it out conveniently, okay, disk. But interestingly, all disks seem to accelerate with the same acceleration, independent of the mass, independent of the radius. Now all of this is fairly curious, I would say. The acceleration does not depend on the mass, it does not depend on the radius. So all disks have the same acceleration when they are rolling without slipping, and a particle in comparison is going to accelerate much faster, right? So what about method 2 and method 3? Well, I will definitely make a video on this, but I hope your curiosity is sufficiently whetted to go and read this. And believe me, it's easy, interesting. You should get the same answer, and it'll give you insight into the subject, into the topic that we are studying. So this is a good time to halt this particular lesson. But I'm definitely going to get back to you with the continuation of this problem with the so-called method 2 and method 3 from this book. Plus, we have another version of